Okay, so the notes for today. All the images that are on here, you can go ahead and screenshot. Make sure you crop them out, don't have any extra words or anything on there, and then you can put those in your notes. If, of course, you'd rather print your notes out and then write them out, scan it and upload, that is fine also, all right? But do pay attention to the deadlines for the notes. You have these notes for beat frequency. They are due, actually this and the lab that you will be doing, they are both due Monday night. So please make sure that those are both completed. All right, so I'm going to go to the notes. Okay, so we have been talking about some of the characteristics of waves. We had talked about interference a little bit in terms of slinkies. So if you have, we use the slinkies as an example. So what would happen is if you had a wave coming down, moving down, and then a wave coming back, and what happens is they are the same frequency and they overlap, then what happens is you can have either constructive or destructive interference. So here, now we're going to be applying it to sound, since we started sound last time. So in phase, when wave frequencies line up in the same direction, what they're going to create is called constructive interference, all right? So here you have two pictures of two waves that overlap. The amplitude here is 2 for this one, where the crest is. Amplitude here is also 2. That's the top, the crest. And what happens are, as you can see, the frequencies are the same, so they overlap, okay? They overlap perfectly. So what happens is when they overlap, since it's only energy that gets transferred and not matter, the energy is able to overlap. What'll happen is, since they are in phase or facing the same direction, they will build on top of each other. That's called constructive interference. So your amplitude is going to increase. In terms of sound, what that means is that their sound is going to get louder. So when I turn the volume up on my radio, what I am doing is I'm actually increasing the amplitude, okay? So the same thing here. When you increase your amplitude in terms of sound, that means the sound is going to get louder. Now, on the other hand, what happens is if you have two frequencies, okay, same frequency, but what happens is they are out of phase, which means they're opposite each other. So out of phase, wave frequencies are exactly opposite each other and lined up to create what's called destructive interference. Rather than building on each other, does everyone have this? Did you screenshot this so you can add this to your notes? Or you can draw with Cami. Yes, you can draw it on Cami. But you may want to screenshot this for later in case you need it. Just so you have it. But of course, you'll have this recording also to go back and review if you need any information here. All right, so for this one, they were in phase. Okay, lined up, facing the same way. And what they do is they build on top of each other. In terms of sound, you increase your amplitude. In terms of sound, the sound is going to get louder. Out of phase, what happens is rather than building, they cancel each other out. So what you have here is a picture of two waves that are of the same frequencies again, but as you see that they are opposite each other. So amplitudes are equal but opposite. Okay, same here for the trough. There's a trough here, there's a crest here, but they're equal amplitude but opposite of each other. What happens is since these are all out of phase, you're going to get cancellation or destructive interference. Now, since the amplitudes here are all the same, you get what's called complete destructive interference. 100%, all of it's going to cancel out, all right? But if you have, you can also get like a partial cancellation, a partial destructive interference. So maybe they line up, but the amplitudes are not the same, all right? So the loudness is not the same. What'll happen is you will only get partial, which destructive interference, which means the sound is going to get softer. Rather than being completely silent, this, in terms of sound, means silence. You're not going to hear anything. So noise canceling headphones. But if if the amplitudes are not the same, then what happens is you have, again, just a partial destructive interference, which means just the sound is going to be softer, all right? It won't be as loud. We're going to pause a moment and listen to a video which will demonstrate a constructive and destructive interference in sound. That's this link right here. This link, I believe, you have in your notes, and this one is something that you can actually try at home if you have earbuds. So let's go ahead and take a listen to the video and listen for that destructive and constructive interference in sound.
Okay, this is a demonstration of interference patterns produced by two speakers. This signal generator is generating a tone that's at about 2,000 cycles per second, 2,000 hertz, and it's sending the same signal to both of these speakers. And if you're out in front of those two speakers, then what matters is the distance from you to one speaker compared with the distance from you to the other speaker. If those two distances are the same, then the sounds that are produced by these two speakers overlap and interfere constructively. They add together to form a louder sound. But as soon as you've moved a little bit in such a way that the wavelength, that the difference between the two paths, between one speaker to you and the other speaker to you is half a wavelength, then instead of the peaks and the valleys overlapping with each other, you get a peak where there's a valley in the sound, and the sound cancels. That's called destructive interference. And so what we're going to do next is to use this microphone attached to this meter and move through the sound field, and you'll be able to see with your eyes on the meter the level of the sound, as well as hear the sound picked up by this microphone that shows this constructive and destructive interference pattern. Okay, right now we have this microphone that's picking up the sound from those two speakers, and we're right symmetrically located in the center between the two speakers. So what we'll do now is to move away from the center, and this readout here gives the loudness of the sound that's picked up by this microphone. And as we move through the interference pattern produced by these two speakers, you'll be able to both hear the sound from this microphone, which will be louder, then softer, then louder again as we move through constructive interference to constructive destructive interference. And then you'll also be able to see that that the readout will show that loud, soft pattern. So I'm going to be quiet now so that the microphone will just pick up the sound from the speakers. Okay, we went through about 3 or 4 different minima and maxima, and hopefully you were able to hear that the sound is changing in loudness.
Okay, so as you heard, what happens is depending on how your waves overlap, you can have a decrease in the sound, the loudness of the sound, which is destructive interference, or you could have an increase in the sound, which is your constructive interference. Okay, but we're talking about frequencies that are the same, so they're overlapping. Now, what would happen if your frequencies were slightly off? What would happen if your frequencies were slightly off? So how many in here? You can just say yes in the chat or raise your hand or something for those of you who have your cameras on. How many are in band? How many band people do I have in here? I see one hand. Nothing in the chat. Two students. Anybody else in the band? Okay, so before you actually start to perform for someone, what does your band instructor do? What does he have you all do? As a band, what do you do before you start playing, before you start your performance? You don't just all show up and start playing, right? Everybody show up for a concert, you tune. You got to tune up. So what does it mean as far as tuning up? What are you trying to do? Tuning means how do you want to sound in relation to each other? Do you want to sound the same? So if you play a tuning note, do you want everyone to sound the same, or you want them to sound different, like slightly off? Okay, so you want everybody to be in tune, all right? When you're in tune, that means your frequency, the frequency that you're playing is the same. It's got to be the same for everyone, okay? If your frequency is slightly off, then what happens is when you're playing together, it's going to sound what you call out of tune, all right? So it's not going to match completely. So what we're looking at right now is, and depending on how far off you are, it's going to create something, or it can create something called a beat frequency. So when your frequencies are slightly off, you get a beat frequency created. And it may not be very obvious, okay, but you can hear that something is not quite right, all right? But the greater the difference between the frequencies that are being played, the greater that beat frequency is going to be. And it's called, as far as what you hear, it's called a wobble. So beat frequency, a beat. Interference of waves of slightly different frequencies. You all should be writing your notes. Traveling in the same direction. So it's perceived as a variation in loudness. Interference of waves of slightly different frequencies traveling in the same direction, perceived as a variation in loudness. So it sounds like it's getting loud, soft, loud, soft, loud, soft. That's called a wobble, okay? And that's due to those beats. That's due to the frequencies being off, slightly off. So variation from soft to loud and back to soft sounds like a wobble. Loud, soft, loud, soft, loud, soft. And the number of beats corresponds to the differences in the frequencies. So 1 beat difference means a difference in frequency by 1 hertz. If you hear 2 beats, then what that means is that there is a 2 hertz difference, all right? And when we say beats are like how many wobbles you're hearing per second, all right? Per unit time, per second is a wobble. The greater the difference in the frequencies that are being played, the greater the beat frequency is going to be. So what I have here in front of me, these are called resonance boxes. All right. If you've ever used a tuning fork, tuning fork by itself doesn't make very much noise. You hit it against something and then you have to hold it up to your ears so that you can hear the sound that it's making. So what a resonance box does is you just basically have a tuning fork attached to this, similar to an instrument, guitar, your flute, any instrument. It's got that hollow opening, right? Instruments have that. And what it does is it allows standing waves to form in there, which amplifies the sound. Okay, so it increases the intensity. So that what happens is I don't have to hold the tuning fork up to my ear to hear it. All right, this is going to be loud enough to hear without holding it up to your ear. So, for example, can you all hear that? Okay, so now let's use these two, and we're going to pretend these are instruments. Now, what you said is that when you are in band, before you perform, what you are trying to do is tune up. And you want to make sure, that the sound is the same for everyone. Your frequency is the same for everyone. Okay. I don't know if you can hear it. Those are pretty close, but they're not exactly on. So the frequencies are slightly different. Okay, really, really close. Okay. Now, what happens is as your frequency, if somebody is out of tune, if someone's flat or someone's sharp, then that means as far as whatever frequency is being played, when they're playing, their frequency is slightly off, all right? It's not exactly what it should be. So listen to what you hear. I'm going to make it obvious. So changing the frequency here, listen to what you hear. Y'all hear that? Do you hear that kind of increase? It gets loud, soft, loud, soft. Does it sound like, as far as that loud, soft, that variation in loudness and softness, does it sound like it's really fast or is it really slow? Fast or slow? Okay, how about compare it to this one? What you just heard, let's compare it to this one. So is this one that I'm about to play, is this faster or slower? This one's slower. What happened was I brought the frequency of this one. Changing this, I'm changing the frequency when I move this up and down. All right, it's actually, the frequency is closer to this now. So the closer the frequencies are, the slower your beat frequency is going to become. Ideally, what's going to happen is you are going to continue to get them closer and closer and closer until you don't hear that wobble. So the wobble should get slower and slower until, see, that's a little bit slower. You can still hear the wobble, but you keep doing that. Tuning instruments, you're trying to get rid of that wobble. All right? The bigger the difference in the frequencies, the faster that wobble is going to get. Sometimes it can get too fast. You actually can't hear the wobbles because they're so fast. It just sounds like noise. It's really bad. All right? It just sounds really bad. Can y'all hear how fast that is? Okay, doesn't sound good. All right, so those are wobbles. Again, repeating. The bigger the difference in the frequencies, the further apart those frequencies get, what happens to the speed of the wobbles? Do the wobbles get faster or slower? If the distance, the difference between those frequencies gets bigger, what happens to the wobbles? That's the opposite. Make sure you write this down somewhere. The greater the difference in the frequencies, the faster the wobbles are going to be, the more wobbles you're going to hear per unit time. Okay? The closer the frequencies get, the fewer beats you're going to hear. So you're going to have fewer wobbles. All right, in this YouTube video, what this is doing, it's actually similar to what we did with the resonance boxes. All right, this is going to, this program is called Audacity. And what you can do is you can actually put in what frequencies you want to play and listen to the difference in the wobbles. All right, so what was just done was you played just a 436 hertz frequency, single tone, and now what he's going to do is go in and change the frequency to, I believe it's a 440, and play them both at the same time. So you have two frequencies that are slightly off being played at the same time. This is a little further along in the same video, so what he's going to do is add on another frequency of 444 hertz. Now, if you look at the difference in frequencies between 436 and 440, which we heard previously, compare what this sounded like to what the 440 to the 444, when these two are played together, what this sounds like. Looking at the values, 436 and 444, there is a 4 hertz difference here. 440 to 444 is also a 4 hertz difference. So as you can hear, even though this was a lower frequency and this is a higher frequency, when you play these two together or you play these two together, the frequency differences, the beat frequency difference is still the same. So as far as what you hear in terms of the number of wobbles or beats is going to be the same. All right, so taking a look at the problems that are here. First one says a piano tuner using a 392 hertz tuning fork to tune the wire for a G natural hears 4 beats per second. What are the two possible frequencies of vibration of this piano wire? Okay, so as we were just saying, what happens is you have your beat frequency is your how many beats per second you're hearing. So we have, let's say, F1 is 392 hertz. And what they're asking are what are the two possible vibrations, other vibrations that would cause this 4 beat, for the beat frequency that you're hearing, 4 beats per second. So we're looking for this, and we know that our beat frequency is 4 beats per second, which is 4 hertz. All right, so this is what you're looking at right now for the problem. The equation for beat frequency is it's the absolute value of your F1 minus your F2. Okay, that is your equation for your beat frequency. We know what the beat frequency is. We know what this is. So basically what happens is when you are solving for your F2, you're going to have your 392 hertz. All we're trying to do is produce a beat of 4 hertz, 4 cycles per second, 4 beats per second, all right? So that can be, as far as what frequency is played with this, there are two possibilities. So you're going to add and subtract plus or minus whatever your beat frequency is. Okay, it doesn't tell us if what was played was a higher pitch than the 392 or a lower pitch. So that means there's two possibilities. So 392, sorry, that should be 392 hertz. Don't forget your units. 392 hertz plus or minus 4 hertz. So what are the possibilities? What are the possibilities for F2? Go ahead and put it in the chat, please. So 392 minus 4 is, yes, 388 hertz is a possibility. And then what's the other possibility? 396 hertz. Okay, so when you are doing problems like this and you are given a beat frequency, that means as far as whatever frequency you're solving for, there are two possibilities. You cannot narrow it down unless they let you know some other information. Like if they said specifically that the sound that was heard or the pitch that was heard was higher than the 392, then we know that has to be 396. If it was said that the pitch was lower than the 392, then we know it's 388. But if all you have is a beat frequency, then you know that there's two possibilities, okay, for the other frequency that was played. Yes, so there will always be two solutions for the other frequency unless you have other information to go on. All right? All right, let's take a look at the next problem. Okay, second one said a frequency of 440 hertz and 446 hertz are played simultaneously. What is the beat frequency? Okay, so for this one, we know F1 is 440 hertz. We know F2 is 446 hertz. And you are looking for the beat frequency. Beat frequency equals, equation was up here, the absolute value of F1 minus F2. So this would be 440 hertz minus 446 hertz, absolute value. So what would the answer be? 6 hertz. Any questions on those two problems? All right, that ends it for your notes. Let's go take a look at your lab